Hey class, Adam Ward here. Third example on how to use dimensional analysis. And so in this case, we're going to look at flow through a contraction in pipes. And this was actually one of the early applications of dimensional analysis. All right. So we're given a situation where we've got a pipe in which you're looking at a cross section here drawn in black. We have diameter 1 on the larger part of the pipe, diameter 2 on the smaller part of the pipe with a sudden step change in diameter. We've got a pipe flow velocity V coming through the pipe, a fluid with a density and a viscosity, and a pressure drop associated with this. And you'll remember from our coverage of the Bernoulli equation and energy equation, what that really means is that we're losing energy and we're losing it in the form of pressure. So the challenge here, as with all of our Buckingham Pi problems, is find the dimensionless terms that describe this problem. Or let's simplify down from a solution space that has pressure drop as a function of 5 variables. Let's see if we can't find a reduced complexity way to express this. If you've watched the previous 2 videos, you've seen me take a lot of time and care in laying out each step. For this third problem, I'm going to try to streamline my recording a little bit and leave a little bit more space for you all to help connect the dots or fill in the gaps as you practice. So as we get started here, just a couple of notes. One that I think is important here, we've got this velocity V on the left hand of the image, right? Pipe flow velocity. How come we didn't set this problem up with a velocity 1 and a velocity 2? And the reason is, as we formulate the problem, we think about the geometry of the problem, the external effects like the velocity, and the fluid properties. Those are kind of the 3 big pieces that we want to keep track of. So why not use V1 and V2? It would be redundant. So a velocity in the smaller portion of the pipe could be calculated directly from a knowledge of velocity on the left-hand side and the 2 diameters. Right? So bringing velocity 2 to the problem doesn't add new information. It's redundant with the other variables that we've selected, and so we've chosen not to use it. In a similar fashion, you might ask, well, Adam, why did you pick density instead of specific weight, or why don't you have both? And again, those are redundant. Density and specific weight are, of course, related by the gravitational constant, and so it would be redundant to use both of those. Similarly, we don't use both dynamic and kinematic viscosities. We just express that one way for our problem. So that's all about problem formulation. That's not a step that we've asked you to do in this class, but if you're taking this on for part of a research project or an independent analysis, that's something you might think about. Okay, so as I said before, these 3 groupings of variables, geometry shown in orange, external effects in purple, and fluid properties in green. All right, folks, here we go. Let's list all of the variables involved in the problem. Easy peasy, that was given to us. Let's list the dimensions associated with each one. And so you can see here, the easiest dimensions for me to think about in this case are written. I take a look at this and realized, oops, I actually wrote density in the MLT system. So I'm going to solve this one in FLT. So I'm going to use force instead of mass for my units. And so density actually has somewhat complicated units in FLT. You get force times squared per length to the 4th power. All right. Third step, how many pi terms do we need? Well, we have 6 total variables minus 3 dimensions, so we have 3 pi terms. And if 3 of them are going to be pi terms, that means we need 3 repeating variables. So I'll go ahead and do my selection. I'm going to pick my anchoring variables in green. Why did I make these choices? I picked delta p because it is the left-hand side, so it's always going to be an anchoring variable. I picked density because it has complicated looking units, and I like to save the simpler units for my repeating variables. And I picked diameter 2 because only diameter 1 or 2 should be used as a repeating variable. That criteria of do my repeating variables look different from one another prevents me from picking both, so I arbitrarily picked diameter 2. You could have just as easily picked diameter 1. With those anchors selected, repeating variable wise then, I'm left with diameter 1, velocity, and viscosity. And again, we want to check, do those include F, L, and T? Yes, they do. Do they look different from one another? Yes, they do. And did I pick the simpler variables, which is my preference, not a requirement? Yes, I did. All right, so we've now selected our anchoring variables in green and our repeating variables in red. And I've already reminded you all that D1 and D2 don't look different from one another. That's why they couldn't be used as both as repeating variables. All right, select repeating variables. Done. Did it on the last slide. Form a pi term. So as always, we'll set up our generic equation and we'll start with that first anchoring variable from the left-hand side, the pressure drop or delta P. And we've got that set up as a function of our 3 repeating variables raised to the A, B, and C powers. We write that equation now using its fundamental dimensions rather than using the variable names. Hopefully this is starting to get comfortable. If you've been following along, this is the 3rd video you're watching me do these exact same steps. So for force, we can write one equation. For length, another. For time, still a third. And you'll notice here that in contrast to previous videos, I'm not showing you all of the zeros that would be written in this equation. And I'm not breaking it out by term. That's something that you could do on your own. But I'm just trying to give you some of the major signposts here to make sure that your work is starting to look like my work. We have a system of equations that we can solve. I get a value of A equal to 1, and I get both B and C equal to -1. So my first pi term looks like this. My pressure drop multiplied by that first diameter in the numerator, and in the denominator, velocity multiplied by viscosity, V times mu. Repeat that step for the other anchoring variables. So here's where you all are going to continue to do a little bit more of the work, and I'm going to show you some of the results. For our second pi term, same setup as always. You should be able to get these 3 equations for F, L, and T to look how I've written them in red on the screen now. And you can see my solutions for A, B, and C for those exponents. So I find a pi 2 term that looks like diameter 2 normalized by diameter 1. So again, I want to emphasize here, I'm not showing you all of the steps as explicitly as I have in the past. I'm hoping that at this point I'm providing you with a couple of places where you can check in, and on your own you are pausing the video and making sure that you can actually work through these steps and get to the same pi term that I get. With that same spirit in mind, here's our setup for pi 3. This would be the appropriate place for you to pause. You would write down that fundamental equation, so you'd have force to the 0, length to the 0, time to the 0 on the left-hand side, equals, and you'd fill in the right-hand side using the fundamental dimensions for density, diameter 1, velocity, and viscosity. You would formulate 3 equations, one for the force, one for the length, one for the time, and hopefully those would look like I'm providing you here. Again, you would solve those to find out those exponents of A, B, and C. And you would have a pi 3 term that looks like density times velocity times diameter 1 over mu. And for those of you keeping track, once again, what you've recovered here is the Reynolds number, which is one of those really common dimensionless variables that relates our fluid properties, our kinematics or our velocity scale, and something about the geometry or the length scale of the problem. In this case, D1 takes that geometry or length scale position. with 3 pi terms, we should check our work. So for our first pi term, here's what I get on the right-hand side for fundamental units. I'm just showing you where each of those came from. Forces cancel out. 3 lengths in both the numerator and denominator. 1 time scale. Yes, that one is unitless. We can do the same thing for pi 2. Length per length, that's unitless. We're happy. And pi 3. So pi 3 we recognized as Reynolds number. If you go back and watch the video where I introduced dimensional analysis, I proved to you that Reynolds number was dimensionless there. If you are doing this in your homework or on a quiz or on an exam, you still ought to be able to go through those steps to prove to me that Reynolds number is indeed unitless. I suppose if you recognize it as Reynolds number and you say, I recognize this as Reynolds number, I know it's unitless. I agree with that, but it's good practice to check as you work through these problems. So pi 1, 2, and 3 we are happy with. Leaves us just one last step, which is to express the final form of the equation. And I apparently have not written that out yet, so we'll go ahead and do that here. So our first pi term, pressure change over diameter 1 divided by velocity times viscosity is equal to some function of d2 over d1 and Reynolds number, rho v d1 over mu. So our final answer here, written in red, boxed in red, that's the relationship that we were after. And once again, we've taken a relationship that used to include 6 variables and we've described it now as 3 groups of variables. That simplifies our parameter space and helps us understand what's really controlling the behavior of the system. All right, class, I hope this helps. This is example 3. This is the last one that I'm going to talk through. From here, you are on your own to practice your Buckingham pi theorem. Hopefully this finds everybody well, and I will see you back for our next lecture, which is going to be about similitude and modeling, or what the heck do I do now that I have these dimensionless groupings. Thanks all.